Okay, cool. So, just to start off here, just go here. Can I click? Maybe not.
Okay, all right.
What? There we go. Okay, so, oh, there it is. So, kind of what we've been doing for the last, I guess, 2 to 3 weeks is just this first step right here, the data collection process, right? That just involved, getting the data, getting the information, our main ingredient for machine learning, and trying to, fix it up, trying to clean it, trying to structure and all that good stuff, and essentially preparing it so that we can feed it into this big machine learning model we have right here. Now, we haven't even touched upon this in weeks because it kind of, required some prerequisite knowledge. Now we're finally in this area. So today, roughly speaking, we're going to be talking about this, whole red block here, that involves stuff like training your data, making a prediction, checking the cost or the loss, as some people say, then checking if what the machine predicted was correct. If it wasn't, how wrong was it? And in the case that it was wrong, how do we optimize the machine learning model to make it better and hopefully get the prediction right next time? And then that cycle keeps on going and going until you run out of space on your RAM. That's just kidding. That's EP step wrong. Yeah, then we'll talk a bit more about the final model, stuff like overfitting, how do you deploy something in the real world, and stuff like that a bit later. But yeah, that's what we're going to be doing for today. Yeah. So essentially what we're going to be talking about, at least this semester, is classification. Essentially, well, first of all, let's just go over a problem of classification in the, matter of just a human being. Okay. One more? That's it. Yeah, so let's think about how a human will look at this image and try to figure out what it is, like what is inside this image, right? Well, essentially, how your mind works is that you would kind of like, implicitly split this picture up into, certain features, certain attributes. Some of those features might be the leaves right over here. Another one, maybe this thing has a pointy tip at the bottom. Another thing, maybe it has seeds on the outside. And the other things might have like, shiny surface. So, putting together all those features or attributes, your brain essentially summarizes that and analyzes it and does all that wonky stuff that brains do and say, hey, these must be strawberries because, I've seen stuff with these types of attributes and these types of features before. Therefore, it must be a strawberry. So that's how, we would identify something just, from our minds based, partially on previous experience. Selections. Okay. So essentially, how machine learning works, it works in a similar kind of way, So well, before that, let's go over what we're used to, what traditional programming is. What we're used to is, when we create a program, we create rules, conditionals, while loops, all that good stuff, and then we design a program based on those rules, and then we feed the program data, like, if you want a program to say how old you are, you'd probably, make some syntax saying like calculating based on birth date, just mathematically calculating how old you are in years. So the data would just be, your birthday, then your traditional programming, all that code stuff, good stuff, you get an answer. So like if I say, I was born in 2001, your program would, use those rules to output an answer saying I'm 21 years of age right now. Next slide, please. So machine learning, we have things kind of, worked around a little bit. So instead of, the answers at the end, we already have some answers at the beginning, and we feed it data, and then through that data, we want to get some type of collection of rules or some type of collection of, procedures. And what we do with these rules and procedures is that we use them to further answer some more questions so that we, get more answers, right? So, next slide. So there's several different types of machine learning that we have here. So first off, we have supervised learning. Right here it says, given the labeled data, find the link between the features and have the label to classify. So, quick thing. Whenever you talk about a label, the label is essentially the answer to a question. So if you remember way back, maybe meeting 1 or 2, I mentioned that there's this data set called a Titanic data set. Essentially, it was made out of, yeah. All right. So if you remember, that data set was made out of rows, and the rows contain features of passengers that were on the Titanic. So those features are stuff like age, where they were located on the ship, their, their ticket in some way, I think gender is one of them too. And then all those were columns, and the last column of that data set was whether the answer to the question, did they survive on the Titanic or not? Thank you, Philip. So the label in this case was the answer. Did they survive or not? And that was just a binary response, yes or no. So that's just clarification of what label means. So that was an example of supervised learning. Because essentially, we have this data set with all the features and those, their associated labels. So, maybe the machine identified patterns, like maybe passengers located on upper decks of the ship, the features, that would suggest their location of the ship. Maybe every time you have someone on upper deck, the machine would probably classify as that person surviving because they probably got to escape faster. So essentially, that's pretty much what I'm saying here. Just find the link between the features and labels and use it on unseen data to classify it. So in this one, we have the answer already. On the other hand, unsupervised learning, we're given data with no labels. And so just imagine the same data set, the Titanic one, except we didn't have that last column saying whether they survived or not. In that case, you'd have to, identify patterns and clusters and all that good stuff. Then the last one here is reinforcement learning, create real-time data from a live environment, decide on the best action to take. So we're going to be focusing on this one this semester. So depending on who you ask. So the big question here, right now I've just been throwing out vague, words and just assuming you know what they mean. But what do we actually mean when we say machine learning? How does machine learn actually? Next slide, please. So the thing is that there's a big difference between the ways machines learn and the way that we learn. So the thing is that computers at the end of the day are just based on numbers. They're not, the way our brains work is that I couldn't even explain it to you, but it's just so complicated. It's different, a lot of different things. But at the end of the day, machines learn based on numbers, right? So what is a mathematical concept that you may have come across before that allows us to bridge the gap between an input data and an output data? There's a pretty central thing in mathematics that we use to map something from an input to an output, and that's what machines learn. Does anyone know? Yes. Yes, the function is actually right here. Yes. But anyways, the way that the machines bridge the gap between the data and predicting on new data is the function. The function is what we call models. So, like I said before, learning is essentially based on previously observed data. The machine's going to learn pattern and all that good stuff, and then it's going to adjust its parameters, going to adjust its rules to make a model or a function that will hopefully predict on new data, right? And throughout this whole entire process, what we're trying to do, the key component, is that we're trying to focus on minimizing error, or in other words, we're trying to focus on minimizing the number of times that the machine gets an answer wrong, it predicts something wrong. Like if, for example, we're making a machine learning model to predict the stock price of, I don't know, Apple tomorrow, if the, machine predicts that Apple's share price is going to be, I don't know what the exact figures are, but just let's just say,
For example, that's obviously
yeah,
like, if it predicts something close to Apple's price, we're not saying that it needs to be exactly, that's why we're saying minimize and not, completely get rid of. But if it predicts something that's like, say, close to whatever Apple's share price is, then we know that our model is actually useful because it's within our certain margin of error that we have. However, yeah, if it predicts something like $5 or if it predicts like $1 million, then in both cases, it's clearly like very wrong because it's not an accurate representation of what the scenario which we are trying to model.
yep, exactly. Unless, the stock for some reason just crashes into oblivion
I
tomorrow.
don't think it would ever crash with what you thought.
Hey, you never know.
That would probably be hard, but anyway.
Capitalism. Anyways, any questions so far? Anything I just said? I've just been talking about a lot of words, so could go over it. But any questions, any concerns? Even if it's something, unrelated. Anything? Yeah. Okay. Huh? I mean, it depends on how unrelated they are. It was okay. I got up at like 10 a.m., which is a bit late, but I had some boba tea, so yeah.
So, is the error going to be different for like different areas when we acceptable error? So,
So if we go into like specifics of it, the way that it does that is like you have a method of finding the error, and then the whole goal is, I think you guys, I'm assuming some of you are taking at least like single variable calculus, if not, don't even worry about it. But the whole goal is just to try and use all of those techniques to find the minimum of that error with respect to whatever function you're doing. But the whole goal is in general, like that whole margin of error that we have is not really necessarily something you hard code in, but you basically take your model that you're trying to fit, right? And you're trying to find the parameters of that model. And you plug it into this error function and you go for the point at which the error function is at its lowest. So if you pick a bad model, like say you pick like a really bad model for the problem that you're choosing, right? You could end up with an error, like you could end up training with something that has the smallest error over all the models that you chose. But it could just still have a really bad error. Like for example, if we're trying to train so any sort of classifier on a process that's like truly random, then it's always going to have a lot of error, right? You'll find something that will minimize the amount of error, but it still could have a very large amount of error because just because it's a minimum doesn't mean it's low error range. So that whole margin of error changes depending on like what the task at hand, really. But in general, don't really think of it with machine learning as finding like the best solution overall, but like basically like the best solution given like what you're trying is the idea.
It really does also depend on your data.
Yeah.
If you have like really wonky and noisy data, which we'll talk about probably later, you have to have some tolerance for, a relatively, what may seem high, but maybe, it really also just depends on the context of the problem you're trying to solve. So like in some areas, maybe a 5% error rate is accepted, but it's maybe in another area, that's way too high.
Yeah, I always like to do an example of like stock price versus medicine, right? If you're off by $5 on stock price, right? Or let's not even say $5. If you're off by like 50 cents on like trying to predict the stock price, I don't think that really makes a difference. Now, granted, someone on Wall Street is probably yelling at me, but like as far as I'm concerned, 50 cents probably doesn't make sense. Right? But if we're talking about medicine, right? If we're off by 5 milliliters on like how much how much of some drug needs to invest in someone. If we're off by like 5 milliliters, that's enough to kill someone. So, there are certain fields where you have to actually evaluate the tolerance and be like, okay, if it's off by say like 2%, right? In medicine, that could kill someone. And a stop, maybe not, it may not make that much of a difference. So as Samrat said, it is entirely dependent on the testing. Because, the different error margins can be acceptable depending on how really severe the cost of error is in that test.
Answer your question? Cool. Anything else? Okay. Next slide.
Yeah.
Yeah, so this is just like a formal definition of what a function is, just pretty much what I said.
Yeah, I mean, just basically, sorry. It's just the same thing we said earlier. So you have two sets, right? X is the set of all your possible inputs. Y is the set of all the possible outputs. You want a function that maps from X to Y, and you have training data with X in the set of possible inputs, labels, Y is the set of possible outputs. And obviously, this is just a general notation for a function, right? Just something that maps from one set to another. There can be a million different types of these functions. So we need to learn the best function for this test. And the process of learning that, the process of finding that best function is called learning.
Yes, indeed. And I just also want to point out here that, again, with respect to labels, you can have different types of labels. So you can have binary labels, which I mentioned earlier, which is just, a yes or no answer, like a 1 or 0. Will this certain person default, or in other words, will they be unable to pay back on their loan? That's a pretty common ML question. Or another one is, will the weather be sunny today? Or will the temperature reach 70 degrees today? Again, yes or no question. And then you have other, what's the word for it?
You can also have like multi.
Contiguous.
Or, well, I was thinking that's one. So,
Yeah, that's another thing.
yeah, so there are like mainly 3 types, although that's kind of a misnomer because machine learning. But usually the main types are like, for classification tests, that's not so you can have binary, you can also have categorical, which is just an extension of binary. So instead of yes or no, it's A, B, C, D, or there's also continuous types of learning. So instead of expecting basically continuous learning is basically stuff like if you're trying to do a linear regression or quadratic regression, any of the stuff that you guys want to do, statistics or stuff like that. The whole goal is essentially, hey, I have some data points, but I know that these should actually be from something that is continuous. It's not only at certain X values, it's defined over every real number. And so the idea is from there, okay, well, we want to learn a function that can predict any real number. It shouldn't just predict 0, 1, or 2. It should predict any possible number at all. So yeah, those are the 3 main types. There's also a lot more. You can have functions that predict pretty wacky stuff, but in general, don't worry too much about the specifics about what type of label it is until you're dealing with things like practice. In terms of theory, it's just numbers and stuff.
All right, next slide. So what I was talking about error is that we can actually, formalize that into an actual thing. And the way that we formalize this is that we had functions before that would, solve our problem. But we can also have a different type of function. It's called a loss function. And this function sounds so meta. It basically measures the error rate of the machine learning model or machine learning function. So how wrong is my machine in predicting a certain thing? So if we have a machine learning model that takes, an image of a skin cell and tries to predict whether it's cancerous or not, we would have a loss function telling us how, wrong the prediction rate is. Like how often does it get the, classification wrong? And as in like, if it's given a skin cell that is actually cancerous, but it says that it's a healthy skin cell, that's wrong. That will probably add to the error rate. So the loss function takes care of all that. So, how far off are the predictions? And the thing is, the loss function really does depend on the problem type, whether it's a regression, dealing with real values, 1.165, stuff like that. Stock prices, or classification where it's like discrete values, like it's gonna be 1, 2, 3, 4, but nothing in between, no decimal points. That's the way I like to think about it. Or, another classic way of describing classification is just like, genres of like a movie. You can only have you can't have horror 0.5 or something. It's either gonna be horror or comedy, stuff like that, discrete points. But essentially, your last function is gonna depend on the problem type. And again, we want to minimize the last function. I kind of stole this slide from S2022, but I gave credit. But essentially, I just want to give you a bunch of examples here of really cool things that machine learning can do in real life. So, translation, it can learn from in natural language processing, we call it corpus when we, refer to a lot of documents of words and stuff. So you can have a machine learning model that learns from a lot of different, books of one language and try to in a way, translate it to another. Or you can have a robot for some reason that teaches that cooks from YouTube videos. I don't know why you want to do that, but okay. That's true. That's true.
We're working on stuff that, there are some robots that are not necessarily cooking with this, that do a lot of gas range in the left that has a lot of military equipment, but we have some robots where instead of cooking, it's you look at the way that people move their hands. So you look at a video of someone doing arm exercises or something like that, and you try to replicate that. And those have the ability to be used in places where, so if someone is not able to use their arm, you can have arms that will be able to just do whatever the heck you want with them, because they'll learn the lack of any emotion. So they'll learn how to, say I told her, hey, grab my headphones over here. We'll learn to be able to fix that and grab the headphones like that instead of being
Thanks for the insight. I didn't actually know that.
It's $250,000 piece that someone just handed to me and was like, hey, hold it, it's working with another.
Yeah. Another example is recognizing objects and images. So, for example, just give this, picture to the computer, oh, this is probably a type of flower. Okay, cool. Another one is analyzing genomics data. Maybe you know about this more, Roger?
I don't. I probably don't.
Okay. Do you just do medical stuff? I just assume.
I just happen to, honestly. I work in image analysis. Yeah.
But anyways, in all these cases, we can see a pattern here. In all these cases, what the machine is doing is just learning from experience. It's learning from previous data. This one, it learns from previous YouTube videos it watched. And this one, it learns from previous images it's recognized in the past before. And sure, it's going to get it wrong sometimes, but at the end of the day, if you have a good model and you have, a good optimizer that will point it in the right direction, it's going to get at some point where, it's going to be kind of reliable. And that's, at the end of the day, that's the point. Yeah. So finally, well, it's not the end of the thing, but I just said finally, whatever. But getting away from all of the vague, wishy-washy word things, let's get into specifics. How do we actually, take all this theory and apply it in practice? The first thing that we're going to do is, specify one of the type of models that we use in order for machines to learn. And we're going to be going over decision trees and eventually random forests. But we're going to be starting with decision trees. Now, to preface this, decision trees are probably one of the most used models in industry today. I think in my previous internship, Cap One, a lot of their work was with decision trees and, by extension, random forests, which is just a bunch of decision trees put together and stuff like that. So I think, I can't remember who said it, but I think it was either someone from industry or a professor of mine said that in 80% of industry, decision tree is kind of what companies will try at least first. So it's a very good baseline model. And on top of that, it's a very good model to explain to other people what's going on. And explainability in machine learning is a, I wouldn't say relatively recent, but like it's a growingly important topic that in machine learning that I will talk about at some point. But anyways, to I guess bring about the concept of what exactly a specific tree is and how it actually ties into how we teach robots how to, cook for YouTube videos. So first of all, let's just play a modified version of the game 20 questions. I'm pretty sure some of you at least know what I'm talking about here. But essentially, next slide. Essentially, what we have here, the game goes like this. The person has an object in their mind that they're thinking about, right? And the player has, 20 questions, 20 yes or no questions they can ask the person in order to determine the object that they're thinking about. So, you can just read here, just examples of yes or no questions that the person asked in order to, eventually find out what the object is. So, next slide, please. Let's just play this game here, right here. Nice. Okay, so can you identify the object in this room that I'm thinking about right now using just 20 or less than 20 yes or no questions? Does anyone want to play with me? Yes. So you have 20 questions or less than 20 questions you can ask me in order to identify the object I'm thinking about. It's in this room. Go ahead.
Is it a person?
No.
People are probably expect.
Well, that's one question.
Okay. Is it something attached to the ground?
No.
Is it the projector?
No.
It's hard.
I mean, you have like 17 more questions left.
Is it a light?
No.
Is it attached to the ceiling?
No.
Is it attached to the walls?
No.
Is it on a table?
No.
It's not on a table. Not attached to the walls or the ceiling or floor.
Well, you didn't say floor, did you?
Yeah.
Oh yeah, it's not attached to the floor.
Okay. The trash can.
Yes. So that was like what, 8 questions or something? Oh, okay, congrats. So I'll think of something else. Okay. One more? Anyone want to play? Yes. 20 questions or less.
Is it an object?
Yes.
Is it a chair?
No.
Is it an electronic item?
No.
Is it the light?
No.
Is it something you write on?
No.
Is it something you wear?
No.
Is it something you do?
Yes.
An apple?
No.
Computer?
No.
Mouse?
No.
Keyboard?
No.
Something that
No. You're down to 8 questions now. You're gonna ask attributes about features, characteristics about the object.
Oh, can I ask, like, what are the characteristics of the?
You can ask yes, no question.
So you can ask, like, is it living or is it living?
Yeah, stuff like that.
Is it black?
Yes.
Is it the lamp?
The what?
Is it the lamp?
No. Come on, you have like 6 questions left. You can phone a friend. You can like ask someone for help if you want to.
Is it small?
Yes. 5 questions left.
Does it run on battery?
No.
Is it backpack?
No. 3 questions left.
Okay, can you write on this, on the,
I believe that was already a question, right?
lower question?
Yeah.
Reword this also.
You can only do a yes or no question.
Yes, we wear it, we don't wear it, but.
Oh, you're asking whether you'd wear it?
Yeah, it doesn't.
No, you wouldn't wear it.
We wear it.
No, 2 questions. You can also ask other people for help. You have 2 questions left. So might as well.
And also better question.
Not yet.
Is it expensive?
No. 1 question left. Yes. Wow. Right there.
I couldn't see that.
And it is black. It's not just red. But yeah, wow. You got it on the last guess. Good job. Good job, guys. What's your guys' name? Wait, this you? Keisha and Erwin. Good job, guys. You guys passed the test. Now you get to graduate early. No, I'm just kidding. Next slide. So yeah, essentially what you guys just did there, you were somewhat of a decision tree in that activity right there. So essentially, that's what a decision tree is. It's basically a model that asks yes or no questions to determine what this piece of data its associated label is. So to look at a more concrete example, let's see here. So let's say we have a task where we want to learn to identify a type of animal based on their features. Next slide, please. Essentially, this is what a decision tree would look like for that type of task. So, well, let me go one by one. So the root node right here, right? And by the way, all these, circly things are called nodes, right? The root node is essentially the first question you ask, right? So let's just go one by one. So let's say we have a piece of data, right? I'm just reading off the features of right now. So we go one by one, starting at the root node. We ask a question in the height variable or height column. Is the animal short or tall? Let's say that it's tall. Okay, so we go from here down to this node because we took the tall thing. So we're stuck at this node, and at this node, the question is: does the neck attribute, is it a short neck or is it a long neck? Let's just say that it is a long neck. So we travel down the node and reach this through leaf node. A leaf node is essentially a node which doesn't have any more, place to go. It's just like at the bottom. And no more arrows have gone from it. So at the leaf node, we can reach a decision that this animal right here, based on the data, might be a giraffe. And that would kind of make sense because giraffes are tall and long necks. It's just like, a toy example, so don't take it too seriously. But essentially, what's just happening here is that we have a already constructed decision tree, or in other words, we have an already constructed series of rules or series of questions. So essentially, this whole thing right here is a machine learning model, right? It just looks, a bit more visual, because again, it's more, easy to explain machine learning model. But essentially, this is, one of the ways that a machine can learn from data and predict from new data, right? And just to drill this concept in your heads, let's take another piece of data, for example. Starting the root node once again, I am short. Starting the root node once again. Let's say this time that the height attribute of the animal was short. So you would travel down from this root node to the to this node because it's short. So this guy. And now you ask the question, the binary question, does it squeak? And let's just say that it can squeak. So we go down from this node to this node, and then we can determine that, well, our model predicts that the animal we have right here might be a rat. So as you can see, all these black labels right next to the leaf nodes are the decisions, or the labels, you may want to call it, but one second. Yeah. And all these orange, I think, orange words here are features or attributes. So essentially, what I've been drilling in your heads for the last few weeks is represented right here. And that's the reason I kept on saying it over and over again, because that is essentially all machine learning is, just learning patterns from attributes of data and trying to predict new stuff from it. And I think it's just so interesting. So like the simple concept of learning from previous data can be applied to so many things in, business, medicine, all that good stuff. And so many applications, just, I don't know, fascinates me. But essentially, yeah, that is the basic overview of what a decision tree is. Any questions about that? Okay. You want? Sure. Don't be shy. Okay. Cool. One second. I'm trying to give you 2 minutes. Let me see if I have anything else I want to talk about. There's no feedback form yet. There will be next week. Anything else you want to bring up, Phil, for this topic?
Well.
Yeah.
Yeah, I don't really have much to say about them. They're really useful for scenarios like the one Summer said earlier, so where you have the, whether or not someone survives on the Titanic, well, that's a really easy thing, because you can ask some serious questions, right? So you can start with where they have one entire shot with this, if anyone remembers. So where they won't entire shot, then the likelihood of them surviving is higher, so you can say, if they were, there's a high chance they survive, assuming that. It makes it easy for data where you can separate, the targets based on a lot. You can separate like labels based on a lot of different choices. However, decision trees are not used for regression models.
It can.
In what way?
And it is possible. I'll explain next week.
Okay, cool. Yeah. Well, they can be used for regression models today, I learned, but I did not think so. But I think that's what I know.
Really depends on specific data, but
All right, well, you'll know more things you actually have usually, but you guys don't know I don't use this. You just don't really like that.
they really don't.
Yeah, I know they don't. But like,
That's another important point. Your model, the machine learning model that you pick really does depend on the data. So like for example, for image data, our friend Phil here loves to use CNN as an accomplishment of methods.
There's a lot of different things you can actually use for image data, and I don't want to get start. I don't want to start because once I start, I won't stop talking about that because I want to do my PhD. But with all of that said, as Summer said, it is a very important thing to bring up that the type of task you have does determine the model. So as I said, for things where you can easily like split the data along like short and tall and so on and so forth, decision trees are really good. There are other types of models, if any of you have ever heard of pyoneers models, For those of you that don't know, it's basically just find points and find the distance between things, and you just say, hey, if you're close to that one, then you're close to the same way. Those types of things are really good for data where you can actually just draw a line between them, but it's not necessarily like break it down to like series of choices. In general, the thing you do when you start, when you work on machine learning is you try a bunch of different models on your data set. And part of it is also actually knowing how to do it. So for example, Simon mentioned that I use a lot of images, right? So if I'm using an image, well, I can tell, hey, is there like an easy way to turn this image into something that's like small, right? Like a vector set that I can take percentages into right? Can I turn it into something small? If I can, well, it allows me to use different models. If I can't, if I need to keep the image as an image for whatever reason, then we start opening up things like convolutional neural networks or anything that can operate on like a big matrix and pull out of it. But like different models, even in those scenarios, different types of neural networks, different models will perform better for certain types of tasks. A lot of it also comes down to like like space. So for example, on your phones, right? When you guys are doing predictive people, right? I don't know what model they use, so not. But one of the big stipulations for those models is that they have to be quick, right? You don't want to be typing something and then be waiting 30 years for your prediction to come out, because then it's absolutely useless. But if you're trying to do something, say, like at the Large Hadron Collider, right? All the data needs to be collected quickly, else stuff happens in 100%. But like analyzing the data, unless it's like, but like analyzing the data doesn't need to happen like instantaneously, right? For some scenarios, because in those things like that, especially with the LHC, you're not really doing things on like a time critical basis. It's not like someone's waiting on the output and like needs to continue along with things, or like it's almost been time on it. You're trying to get data so you can publish it in the research. But stuff like, you know, predictive text or like, you know, medical diagnosis models, stuff like that, you need those to happen quickly. And so decision trees, in some cases they can be good, right? Another big thing with decision trees, you want them to be short. Right, so notice how this one here only has like 3 layers. 3 layers are 5. 4, 2, 3, 4, 5. All right, math major, I can count. But like decision, you want them to have like 5 layers. Because if you think about it, in a game of like 20 questions, right, you can see how that can take like a while. And if we send it to say 100 questions, that can take even longer. And then some of those questions start being absolutely useless because you know they don't go. You can ask like you'll ask like 100 different questions. Some of that are just like there's no point in asking. So with specifically with decision trees and with models in general, one of the main things is you want to try and make them small. So when you want to prefer simpler solutions, so models that are smaller, that have less like parameters, that basically the amount of numbers and other things like that. So,
Yeah, I remember what I want to say now. Keep in mind that this is a quote unquote finished model. So this is the result after training with some historical data, and then this tree has already been constructed. What I mean by that is that there's a certain order in which you may want to ask questions in. So for example, this may be getting too deep into it, I want to explain next week, but essentially very high level, at a very basic level, you want questions that are more important than questions that may not be important. So for example, when I'm talking about an eraser, right? You may want to ask questions like, is it expensive? How small is it? Because it's an object. But if you ask questions like, can it breathe underwater? Can it drink water? Those are probably not going to be great, questions to ask. So, and even for this one, if you ask the question, is the animal on Earth? That's probably not a useful question because pretty much all animals that we know, I don't want to, dig on any space folks in here, but any animals that we know are going to be on Earth anyway. So it's a pretty useful question. And the thing is, with the more useful questions, we can split the data more, readily. And what I mean by that is that we can classify the data better, right?
Yeah, I mean the whole idea just goes very deep into training. In general, when you are picking each node, you basically look at the data you have and you go, okay, which attribute, which of the given attributes enable me to split the data in this? So say I have like 10 examples, right? If one of the attributes, or one of the questions I ask splits it into like 5 and 5, then that may be a good attribute, because that allows me to branch out and ask one specific question out of each of them. Instead, but if there's one attribute that say, you know, it splits up like all of the data into one side, if it splits, if it makes a split of like, like eight on one side and 2 on the other, well, that one may actually be a better question, right? And the reason that it's a better question is you've already eliminated 2 classes. Those 2 that you have, they're probably, so you can just be like, okay, cool, I've already eliminated one. And it's like it's a huge thing, I honestly don't really understand.
Occam's razor.
But yeah, let Isaac talk about that.
We'll talk about that later, but any questions on that? Any questions at all? Any concerns? We'll also get into code of this. Don't worry, it's not all in the imagery. We're gonna be practical code too. It's actually pretty easy because, like, if we use libraries, it does most of the work for us. But the main thing is just understanding the concepts, and the code is just like a couple, like 4 or 5 lines at most. It's good practice, for sure.
It is good practice. In fact, if you take 4.1, 4.2, or any of those courses, they will make you great.
Speaking from present experience.
Yeah, but it's not the worst thing in the world, but like when you have the library,
So here are the logistics. So we're eventually going to be splitting you guys up into groups for the final project. So be on the lookout for probably a Google Forms or a spreadsheet that you'll be able to fill up names for. If you guys have friends in club, that's good. If you don't, make friends. Then we'll start putting you guys into groups. I think this semester we might cap it, the number of people in a group, maybe 3 or 4. We haven't exactly decided.
It entirely depends on the amount of people.
Who wants to participate? Yeah.
So, put your name down if you want to be in the group, really, and
Next week we will have a feedback form, the mid-semester feedback form you all fill out. That really does help us out, make this semester better, make the club better overall. It also, informs us which room to rent, for example, for next semester, whatever. It also, you can literally just be honest as possible. If you think I'm a boring piece of shit, saying I'm a boring piece of shit, I really don't care. It helps me. Helps. If you think Philip's a piece of shit, Tom, piece of shit, I really don't care. Point is, be candid as possible because it really helps us. I don't have my feelings hurt that easily, so I'm already dead inside. But yeah, that's all I have to say for today. Thank you so much for coming out in the cold weather. We'll see you next week. Thanks so much.